and I will share my screen and get over to the right thing. Okay, so we have, counting today, we have 3 class meetings left. We have today, which is the 24th of April. We have Wednesday, which is the 26th, and then we are scheduled to meet next Monday, which will be May 1st. Okay, our topic today is going to be the 1 proportion z-test and the 2 proportion z-test. Then the topic we have left is chi-square goodness of fit. If time permits, we may start that today. I hope to have to finish up the content on Wednesday so that we can dedicate next Monday to kind of a review day. I have a review sheet that I'll put out in the announcements for you to help you get prepared for the final exam. Okay. So today's topics are 1 proportion z-test and 2 proportion z-test. And I'm going to use the PowerPoint to kind of go through some of the explanation, and then we'll come back over to the document to do the examples. This is really not going to be a lot of, hopefully not a lot of new information. We're going to talk about a 1 proportion z-test. We're still doing or still talking about hypothesis testing. We will still be going through the traditional steps of stating the hypotheses, identifying the players, calculating the test statistic and its p-value, making a decision, and writing a conclusion. Those 5 steps for the hypothesis testing process have not changed. Again, what changes is the test statistic that we calculate. So a 1 proportion z-test is, again, really the same process, same procedure that we talked about initially in Module 3 in relation to a 1 mean z-test. And if you think back, when we first began talking about the 1 mean z-test or the 1 mean t-test, I pointed out to you that in the scenario, the story would use the word average or the word mean. In the problems that we're going to be looking at today, it's going to refer to either the population proportion or a population percentage. It's going to be talking about percentages or proportions rather than the mean. So we're just shifting our focus from the mean to either a proportion or a percentage. Some of the guidelines or the conditions that we know to kind of look for using a 1 proportion z-test. Again, as is the case with any hypothesis test, we want to have a simple random sample. Ideally, the population is at least 20 times as large as the sample. So if my sample has 5 values, 20 times that would be 100. So I'd like my population to be at least 100. Now that's not necessarily a very rigid requirement, okay, but that's the ideal. The individuals in the population are divided into 2 categories. Sort of think about it like a yes category and a no category. Okay, a yes and a no. Think about like smoking or not smoking. It could even be right-handed or left-handed. We could do male, female. So where you're going to have 2 categories within the population. You divided them up into 2 different groups. there's some calculus things to think about. The values of n times p and n times 1 minus p are both at least 10. But again, I don't want you to get too caught up in those conditions, because for our purposes, we're going to assume that those conditions are met. Again, if you were doing this in the real world, then you may want to go through and verify those things before you actually conduct the 1 proportion z-test or even a 2 proportion z-test. But again, for our purposes, we're assuming that they're met. There's some different notation, different symbols that you're going to see with a 1 proportion z-test, so I want to introduce you to those. We use a lowercase p to represent the probability of success. That's either the proportion or the percentage that the event occurs, that you get what you want. But guys, be really careful, because that lowercase p is not in any shape, form, or fashion the same as the p-value. I've tried to be very deliberate about indicating p-value and writing the phrase p-value, because I knew this was coming. Okay, a lowercase p represents the probability of success. Success means you get what you want. The probability of success in a 1 proportion z-test is equivalent or is the same as the population mean in the 1 mean z-test that we talked about in Module 3. It is typically written in a decimal form rather than a percentage. We want it as a decimal. And it is usually going to be stated in the scenario. If it's not stated, you are given the information to calculate it. Okay, if it's not stated in the scenario, excuse me, I misspoke. If it's not stated, then we use 50%. And you may say, well, why do I use 50%? Remember, we have 2 categories. So there's a 1 in 2 chance that you're going to fall into a particular category or be success, that you're going to be successful. So 1 out of 2 is 50%. So if it's not stated, the default is 50%. A lowercase q is the probability of failure, which means you don't get what you want. Okay, so proportion or percentage, the event does not occur or you don't get what you want. And together, P and Q have to add to 1 or to 100%. The formula for calculating Q is 1 minus P. Again, it's typically written in decimal form. And it may not be stated in the problem, but I can calculate it. N, lowercase n, is still our sample size. The mean of the population is P. The standard deviation of the population is found by doing the square root of P times Q divided by N over, or square rooted, excuse me. Okay, so you're going to have to kind of get familiar with these symbols. And I'll try to walk you through it as we go through examples so that you'll get familiar with them. The different scenarios that we have for the 1 proportion test is the same as we have for the mean. You can have an equal and not equal, which is your 2-tailed test. You can have less than, which is your left tail test, or you can have greater than. It's the same three scenarios. Which one you have depends on the phrasing in the problem. The instructions for Minitab, okay, let me tell you what slide number they are, is slide number 5. The Minitab instructions for the one proportion Z is slide number 5. And then we're going to get into some examples. So I'm going back over to my Word document just because it's easier to work with them in a Word document format. And we're going to look at some examples. Again, one of the things that you have to be able to do is to recognize, what type problem you have. We've been talking about that off and on really since the midterm, that you've got to be able to recognize which test you have. So if I read this problem, it says, according to CBS News report, New York City's adult smoking rate was 12% in 2021. Suppose that a survey is conducted to determine this year's rate. 9 out of 70 randomly chosen New York City residents reply that they smoke. Conduct a hypothesis test to determine if the rate is still 12% or if it has decreased. Use a 0.05 level of significance. So a couple of things that I want to point out after reading this problem. First off, as I read through the problem, there is no mention of the mean. Okay, nowhere in that paragraph does it talk about the mean or the average. What I do notice is that I'm given some percentages. Okay, so I see percentages or percentage. So that's my clue that I'm probably going to do a proportion. And then I need to think about, should it be one proportion or two proportion? And again, as I'm thinking and reading through this paragraph, they're only talking about one thing, about whether people in New York City smoke or not. So that is my clue that I've got one proportion Z-test. And guys, if you're doing a proportion or a percentage, it will always be a Z-test. Okay, if it's a proportion, it's always going to be a Z-test. So using those clues, I recognize that I need to do a one proportion Z-test. And it does tell me in the problem to conduct a hypothesis test. So my first step is to state the hypotheses. Okay, you're going to have the null and you're going to have the alternative. For a proportion test, we write the hypotheses in symbols. Okay, we write it in symbols. And if I look back through the story, it says conduct a hypothesis test to determine if the rate is still 12% or if it has decreased. Okay, so I see two phrases. I see is still and decreased. So if I'm thinking through what that means, is still to me implies equal, or decreased would be less than. So this is actually a less than or equal to problem. Because equal is implied here, that statement is the null. So we're saying the proportion, we use P for proportion, the proportion or percentage is less than or equal to 12%. Now, I do have to convert the 12% to a decimal. If you don't remember how to do that, you take 12% and divide it by 100%, which gives you the decimal 0.12. That's the value, that's the hypothesis that is given. I know then that the alternative is the exact opposite. So P would be greater than the 12%. And that comes directly out of the problem. Step 2 is we identify the players. Okay. And I don't remember exactly what all we need for Minitab. Let me see if I can look at those instructions and tell. Okay, we need the number of events. We need P. Okay. I want to make sure I tell you what you need. Okay, we need P. We're going to need what's called P prime, N, and alpha. Okay. P is the population proportion, and it's the value that's in your hypothesis. P prime is the sample. It's not really a proportion, but I'm going to write the word proportion. Okay, it represents the number of successes. And let me make a little bit of space in case I have to do some explanation. N and alpha. N is your sample size. And alpha, of course, is your level of significance. And with the level of significance, we could, if we need to, find the confidence level. Okay, so from our story, we know that the population proportion is the 12%. You may need to think about, in this scenario, what represents a success. Okay, because P prime represents the number of successes. Okay, in this case, we're talking about the adult smoking rate. So a success in this scenario is that a person smokes. And they give you kind of in this third sentence, it says 9 out of 70 randomly chosen New York City residents reply that they smoke. So the report from CBS had said it was 12%. So you go out and you choose 70 randomly, choose 70 New York City residents randomly, and you ask them, do you smoke? And they're either going to say yes or no. Okay. The 9 represent the number of successes. You talked to 70 people. That's your sample size. Of those 70, 9 said they smoke. So P prime, which is your sample or your number of successes, is 9 out of a total of 70. And then it says in the last sentence to use a 0.05 level of significance. So if my level of significance is 5%, that means my confidence level is 95%. Any questions about where those numbers came from? Then we're going to calculate the test statistic, which in this case is going to be a Z, and its p-value. We do that in Minitab. And again, the instructions are on slide 5 of the one proportion PowerPoint. So I'm going out to Minitab. Got to wake it back up. Okay, so we need to do a one proportion Z-test. So I'm going to stat, basic statistics, and I'm going to one proportion. One proportion. I have summarized data. The number of events, I had 9 people say that they smoke out of 70 trials. Okay, so let me go over here back to my paper and make you a couple of notes. Okay, in Minitab, your sample proportion is called the number of events, I believe is what they're using. Yes. Number of events. The sample size is referred to as the number of trials. Okay, so I made that notation. I want to perform a hypothesis test, and my hypothesized proportion is the 12%, but you enter it as a decimal. Then I go to options. It is a 95% confidence level, but my hypothesis, the alternative hypothesis was greater than, and we will always do a normal approximation. It's a 95% confidence level. The symbol in my alternative hypothesis is greater than, and you need to change the method to normal approximation. It's just that just tells it what formula to use, and that's the formula we're going to use. I click OK. I click OK again. And again, I have to scroll down to the test. And I'm going to copy this over to my paper. Okay, my test. I get my Z value and my P value. Okay, so my Z test statistic is 0.22. My p-value is 0.413. Okay, you just read those directly from Minitab. Then step 4, as always, is to make a decision. Again, by comparing the p-value and alpha. Okay, so if I do that, my p-value from Minitab is 0.413 and alpha is 0.05. I'm going to compare it digit for digit like we always do. For the p-value, the first number after the decimal is a 4. For alpha, it's a 0. 4 is greater than 0, so p is greater than alpha. If p is greater than alpha, we fail to reject the null. If we fail to reject the null, that means the null is true and the alternative is false. So based on the evidence that I have, the rate is still 12% or it has decreased, because I have proven with the evidence that we have that the null hypothesis is true. So then step 5 is to write our conclusion. So we would say at the 0.05 level of significance, the smoking rate in New York City has not increased. I'm going to say it that way. If it hasn't increased, that means it's either the same or less. So it has not increased from 12%. Now, there are other ways you could say it. If you want to say is still 12% or has decreased, that's fine. Questions? Process hasn't changed. It's just a different test statistic, which requires you to have different information. All right, let's look at another one. It says, a global poll was also conducted by Gallup, and it uncovered that out of the world's 1 billion full-time workers, only 15% of people are engaged at work, leaving a significant 85% unhappy at their jobs. A local flooring manufacturer believes that less than 85% of the company's employees are unhappy at their jobs. A survey of the company's 22,000 worldwide employees is conducted. and 5,200 report being unhappy at their jobs. Use the 0.10 level of significance. What conclusion can be made about the company's employees? Okay, so again, a couple of things to note in this problem. Again, nowhere in this problem there's no mention of the mean. In fact, throughout the problem, you have percentages. They're only really talking about one thing, and the one thing that they're focusing on is employees being unhappy at their jobs. So I have one thing that they're talking about with percentages. So that is my clue that I want to do a one proportion z-test. Now, guys, you have to be careful because this first statement here is like extra information. Okay, they're telling you initially in this first sentence that what the percentage are that are happy. Okay, so this first sentence is kind of like extra info, because then it shifts its focus to those that are unhappy. So you have to be careful when you're reading through this problem to make sure you identify stuff appropriately. So the first step in any hypothesis test is to state the hypotheses. So again, you're going to have your null and your alternative, and these are written in symbols. And so if I read through this problem, it says a local flooring manufacturer believes that less than 85% of the company's employees are unhappy at their job. Okay, this one doesn't explicitly say conduct a hypothesis test, da 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 da. Okay, you have to kind of pick it out from the paragraph. Okay, but remember, when you're looking for that hypothesis, you look for words like believes, thinks, concludes, claims. So it says less than, okay, which makes me think of the mathematical symbol less than, but it does not contain equal. So that statement would be our alternative. So my alternative hypothesis is that my proportion is less than the 85%. Again, I converted my 85% to a decimal. I know that the null is the exact opposite, so it would be that the proportion is greater than or equal to 85%. Then we move on to step 2. Step 2, we identify the players. Okay, you need P, which is your population proportion. That comes from your hypothesis. P prime, remember Minitab calls that the number of events. That's your success. N is the number of trials according to Minitab. Whoops. Sorry. That's your sample size. And you have alpha, which is your level of significance. And then you should be able to calculate your confidence level. Okay, so if I go back to this problem, it tells me that in my hypothesis that 85% of employees are unhappy at their jobs. If I go back to my paragraph, it tells me that the company conducted a survey of its 22,000 employees, and then 5,200 report being unhappy at their jobs. Okay, so we surveyed a total of 22,000 employees, and 5,200 of them said they were unhappy at their job, and it said to use a 0.10 level of significance. 0.10 is 10%, so my confidence level is 90%. I'm pulling all of that information from from the problem. Then the third question, our third step, is to calculate the test statistic, which will be a Z, and its p-value. Again, which we do in Minitab. Okay, we do that in Minitab. So I'm going over to Minitab. Stat, basic statistics, 1 proportion. We had 5,200 employees say they were unhappy in their job out of a total of 22,000 employees. We want to perform a hypothesis test, and our hypothesis was 85% were unhappy in their jobs. Options, it is a 90% confidence this time. We were trying to say it's less than 85%. That's the alternative hypothesis. And we always use a normal approximation. Okay, so we get our test results, find the header labeled test, and we get a Z test statistic of negative 254.90. The p-value is 0. Did I enter that right? Let me double check my numbers. Just seems awfully large. Yep, I entered them right. Okay, it's okay. Sometimes with real data, things can be messy. It's okay. I just wanted to double check myself. Okay, then we're going to make a decision. We make our decision by comparing the p-value to alpha. So my p-value from Minitab is 0. Alpha is 0.10 or 0.10. So if I make that comparison First number after the decimal in the p-value is 0. For alpha, it's a 1. 0 is less than 1. So p is less than or equal to alpha. When p is less than or equal to alpha, we reject the null. So if I reject the null, that means the null is false and the alternative is true. So based on the evidence that we have proven that the percentage is less than 85%. So then the last step of any hypothesis test, including this one, is to write the conclusion. And so we would say, at the 0.10 level of significance, and we may want to use the same wording from our story, so we can go back up and pick that up. The 0.10 level of significance, the employees, let's see, local manufacturer believes less than 85%. Okay, that less than 85% of the companies at the 0.10 less than 85% of the local flooring manufacturer employees are unhappy at their jobs. Questions? Hopefully it's not anything majorly new to you. Again, we're still just conducting a hypothesis test.
Is there one more example?
I don't think I have another one on that lesson.
Okay.
I don't have one on the PowerPoint.
Okay.
I might could pull one. Do you need to see another one?
Yeah, so like just to clarify or make sure.
Okay, let me see if I can find one. Give me just a second. I'm gonna stop the share for a second so I can navigate around without y'all seeing
Okay.
everything. Okay, I'm still looking. Give me just a minute.
Okay.
Okay, I found one. So I'm going to pull it over here into our document and make it larger. Okay, so this one says, a teacher, oops, let me share my screen. A teacher believes that 85% of students in a class will want to go on a field trip to the local zoo. She performs a hypothesis test to determine if the percentage differs from 85%. The teacher samples 50 students and 39 reply that they would want to go to the local zoo. For the hypothesis test, use a 0.01 level of significance. So again, if you're thinking about this problem and reading through it, again, the first thing that kind of jumps out at me so that I can identify that this is a one proportion z-test is, again, nowhere in this story, in this paragraph, is there a mention of the mean. In fact, I have percentages, which is the big clue that it's going to be a proportion. And I'm only talking about one thing. The one thing I'm talking about is going to the zoo. So again, that leads me to recognize that I need to do a one proportion z-test. So we begin the process. Step one is to state the hypotheses. Now, again, this particular one I noticed is not maybe as obvious because it doesn't say conduct a hypothesis test to blah, 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 blah. But it does say she performs a hypothesis test to determine, there's my key word, if the percentage differs from 85%. So I see the word differs. Differs means it's not the same. Mathematically, that would imply not equal. And if it's not equal, that makes it the alternative. So we're saying that my percentage differs or does not equal 85%. And that's the one that's given. If the alternative is differs or not equal, then that means the null has to be equal. Step two is to identify the players. You need P, which is the population proportion from the hypothesis. You need P prime, which is the number of events, which is your successes. You get what you want. N is the number of trials. which represents your sample size. You need alpha, which is your level of significance. And then you need your confidence level. So my population proportion is the 85% because the teacher believes that 85% of her students would want to go to the local zoo. So then I'm going back up to the story, and it says she samples 50 students and 39 reply that they would want to go to the local zoo. So our sample size was 50. Of those 50, 39 wanted to go to the zoo. And it says use a 0.01 level of significance. 0.01 is 1%, so my confidence level is 99%. All of that information is being pulled out of the problem. Step 3 is to calculate the test statistic, which is a Z, and its p-value. So I'm going to Minitab. Stat, basic statistics, one proportion. The number of events this time, there were 39 who wanted to go to the zoo out of the 50 who were surveyed. My hypothesized proportion in this case does happen to still be 85%. My confidence level is 99%. I'm hypothesizing that it differs or is not equal. And I always use a normal approximation. Okay. Okay. Scroll down to get your test results. For my test, I get a Z value of negative 1.39. So Z is negative 1.39. The p-value is 0.166. I'm pulling those numbers directly from Minitab. Step 4 is to make a decision by comparing the p-value to alpha, which is what we've been doing all along. Okay, that hasn't changed. My p-value is 0.166. Alpha is 0.01. Making that comparison. First number after the decimal for the p-value is a 1, for the alpha is a 0. 1 is greater than 0, so p is greater than alpha. If p is greater than alpha, we fail to reject the null. So if I go back up here to my hypotheses, if I fail to reject the null, that means the null is true and the alternative is false. So based on the evidence that I have, the percentage does not differ from 85%. So then I have to say that in my conclusion. So the last step is to write conclusion. So we would say at the 0.01 level of significance, the percentage of students who want to go to the local zoo does not differ from 85%. Okay, so that actually gives you an example of all three scenarios. We did a scenario where it was less than, we did a scenario where it was greater than, and I just finished a scenario where it was not equal. So you have an example of each one. But guys, the process is not changing. It's still the same 5 steps. Questions?
No questions. And thank you for showing me the last example.
Okay, you're very welcome. Now we're going to switch gears. Okay, that was one mean, or excuse me, one proportion. Now we're going to switch to 2 proportions. Okay, we just finished talking about 1 proportion. Now I'm going to switch gears to 2 proportions, which again is comparable to the 2 mean z-test that we talked about in module 3, where we want to compare perhaps two different groups. Again, the process or the procedure is not changing. We will still state the hypotheses, identify the players, calculate the test statistic, make a decision, and write a conclusion. The process is not changing. Again, our focus shifts from talking about the mean to talking about a proportion or a percentage. So again, when you read the story, you're likely going to be given percentages or a proportion. There'll be no mention of a mean. You're going to have, again, you're going to have 2 groups. Remember, that was one of the kind of the conditions for doing a proportion test. So you're going to have 2 samples. Okay. You're going to take a sample basically from 2 different groups. They do need to be simple random samples that are independent, meaning there's no overlap in the groups. Ideally, the number of successes has to be at least 5. The number of failures have to be at least 5 for each of the samples. And there's kind of a new approach to this that, again, growing literature states that the population must be at least 10 or 20 times the size of the sample. Again, that prevents oversampling and causing incorrect results. Again, we're going to assume for our purposes that those conditions are met. But again, if you were doing this, you know, collecting your own data and doing your own research, you would have to confirm those things. And again, the idea of having your population be 10 to 20 times larger than your sample is kind of a new trend within the world of statistics. But again, we're going to assume those conditions are met. Again, we have the same scenarios that we had when we talked about the two-mean z-test. Again, you can have it with less than, which is a left-tailed test. You can have it as a greater than, which is a right-tailed test. Or it could be not equal, which is a two-tailed test. And again, you're going to have proportion 1 and proportion 2. So you have these little subscripts because you have to know which group you're talking about. Are you talking about group 1 or are you talking about group 2? The keystrokes for doing the two proportion test, okay, the keystrokes for doing the two proportion test are on slide 4. Okay, they're on slide 4 of the two proportion test. So we're going to look at some examples, and I move the examples over to the Word document. Okay, so let's look at this problem. It says, a survey found that 83 out of 100 men questioned preferred computer-aided instruction to lecture, while 75 out of 100 women preferred computer-aided instruction to lecture. At the 0.05 level of significance, test the claim that there is no difference in the proportion of men, and it indicates that's going to be sample 1, and the proportion of women, which is sample 2, who favor computer-aided instruction over lecture. Okay, so a couple of things here to think about. In this scenario, again, there is no mention of the mean. It may not be as obvious that you're dealing with proportions or percentages because there's really no percentages given here. Okay, but they're giving you kind of proportions because they're telling you 83 out of 100 or 75 out of 100. Okay, so I do realize, hopefully, that I have proportions. I actually have kind of two groups that we're focusing on because I have men versus women. And it even helps me to recognize that because it tells me down here to sample 1 and sample 2. How did they decide which one was sample 1 and which one was sample 2? Usually, here's how it works, guys. Whichever group is mentioned first becomes the sample 1. Whichever group is mentioned second becomes sample 2. So if you look in this paragraph in the structure, the men were mentioned first, therefore they're sample 1, and then the women were mentioned second, so they're sample 2. And they're asking them questions about computer-aided instruction. So the fact that I have proportions and I want to compare two groups kind of gives me the clue that this is a two proportion z-test. Again, with proportions, it's always going to be a z-test. So we begin the hypothesis testing process as we always do. We state the hypotheses. And again, in this format, in a two proportion z-test, We state the hypotheses in symbols as opposed to words. So you have the null and you have the alternative. So if I go back and look at my paragraph, it says, test the claim, there's my keyword, that there is no difference in the proportion. See, there's the word proportion of men and the proportion of women. Okay, so no difference in my mind implies they're the same, which mathematically means they're equal, which means that statement is the null. So we're saying that the proportion of men, which is sample 1, is the same as the proportion of women, which is sample 2. And that's the given. If you want to use 1s and 2s, you can. I kind of like using M and W for men and women, but you could do it however. If the null is equal, that means the alternative will be not equal, because they have to be exact opposites. Step 2, you have to identify the players. And really, in this scenario, it helps you if you can set up a table, because you're going to need basically P prime, which is the number of events or successes for the men, which is sample 1, and for the women, which is sample 2. You also have to have N, which is the number of trials, which represents your sample size. For both groups, you still need your alpha, which leads you to your confidence level. Okay, so you got to have the pieces for sample 1, and you have to have the pieces for sample 2. Again, they're given in the scenario. If I go back and read, it says a survey found that 83 out of 100 men. Okay, so I had 83 successes and 100 trials for men. If I keep reading, it says 75 out of 100 women preferred computer-aided instruction. So for women, I have 75 out of 100. Now in this scenario, notice how both samples are the same size, because they don't have to be the same size. They are for this problem, but they don't have to be. It says use a 0.05 level of significance. So my level of significance is 0.05 or 5%, which means my confidence level is 95%. I'm then going to calculate, step 3 is to calculate the test statistic, which is a Z, and is p-value. Minitab is going to do that for you. And the instructions are on slide 4 of the 2 proportion z-test PowerPoint. Okay, let me get this one out of the way. So over to Minitab we go. Stat, basic statistics. Now we have 2 proportions. Stat, basic statistics, 2 proportions. We have summarized data. We have summarized data. And it asks you for the number of events for sample 1 and sample 2. So again, it's important that you know which one is sample 1, which one is sample 2. Okay, let me check my numbers. Sample 1 was men, which was 83 out of 100. There were 83 who said they preferred computer-aided instruction out of 100. For the women, which is sample 2, it was 75 out of 100. Options, we're doing 95%. My hypothesized difference will be 0. We said, let's see, let me make sure because I can't remember. We had not equal in our alternative hypothesis. And let me double check. We're going to estimate the proportions separately. Okay, so it is not equal here. And then estimate the proportions separately. It'll be that way every time. I click OK. I click OK. You have to scroll down to get your results. Copy. Get it where it'll copy. Come on. Okay, so we get our test results. Now, we're going to use, as we have been, use the normal approximation. Okay, we're going to use the normal approximation. So I have found that my z-test statistic is 1.40 and my p-value is 0.163. Minitab does the work. I write the answers down. Step 4. Is to make a decision by comparing the p-value and alpha. And we're doing 0.05. So we would have the p-value is 0.163. Alpha is 0.05. Compare it digit for digit. 1 is the first number after the decimal in the p-value. 0 is the first number after the decimal in the alpha. 1 is greater than 0, so p is greater than alpha. If p is greater than alpha, we fail to reject the null. Okay, those guidelines, guys, have not changed. So going back up to the hypotheses, we fail to reject the null, which means the null is true and the alternative is false. So based on the evidence we have, there is no difference in the proportion of men and the proportion of women who favor computer-aided instruction over lecture. Okay, there's no difference based on the evidence we have. So then, as we always do, the last step is to write the conclusion. So I would say at the 0.05 level of significance, there is no difference in the proportion of men and the proportion of women who prefer computer-aided instruction over lecture. And there you go. Questions on that problem? We're going to look at another one in just a minute, but do you have questions on that one?
No questions. All right, then I'm going to skip down to the next example. It says, bullying is a problem at any age, but especially for students aged 12 to 18. A survey was conducted to determine if private schools have less bullying incidents than public schools. 200 private school students were surveyed, and 13 stated he or she had been bullied. 300 public school students were surveyed, and 38 stated he or she had been bullied. At the 0.05 level of significance, do private schools have less bullying incidents than public schools? So again, you have to recognize that this is a two proportion z-test. Okay, so again, as I read through that, there's no mention of the mean. Again, it doesn't really use the word proportion, and there's no percentages. But again, usually when you see something like 200 or 13 out of 200 said this. Okay, so hopefully you can read between the lines and realize that you're getting a proportion. You have two groups in the scenario because we're comparing private school to public school. So again, hopefully the fact that you've got two groups helps you to realize that you're going to do a two proportion z-test. So we begin as we normally do, and let me make sure I got plenty of space here. Oh, I want you to come down here. Make sure I got plenty of paper. Okay, so step one in any hypothesis test, Ms. Ralston sounds like a broken record, is to state the hypotheses. So I have the null and I have the alternative. So kind of scanning back through this problem, it says, do private schools have less bullying incidents than public? So it says less. The word less makes me think of the less than symbol, which makes this statement the alternative. So we have the proportion of private, which they're calling number 1, is less than the proportion for public, and that's going to be sample 2. Okay, that's the given. If the alternative is less than, then that tells me that the null has to be greater than or equal. But the private is greater than or equal to the public. Guys, those words haven't changed from where we started. Okay, you have to stop and think about the meanings. Then we want to identify the players. So again, we need P prime, which is the number of events or successes. And we need that information for private, which is group number 1, and we need it for public, which is group number 2. We also need N, which is the number of trials, or the sample size. We also need alpha and the confidence level, all of which is given in the scenario. I just have to go back and pull it out. So let me go back up here to the story. It says 200 private school students were surveyed and 13 stated that he or she had been bullied. So we had 13 say they had been bullied out of 200 students. Then I go back and I read the next sentence. 300 public school students were surveyed and 38 said that they had been bullied. So we had 38 say they had been bullied in public schools, but we surveyed 300. Notice the groups are different sizes. It's okay. And it says use a 0.05 significance level. So my alpha is 0.05 or 5%, which means my confidence level is 95%. All of that is coming directly from the story, and it is typically very straightforward. They're not trying to kind of confuse you or mix you up. Third step
is to calculate the test statistic, which is Z, and its p-value. Again, Minitab does that work for us. Let me check my numbers before I go over. Okay, so going over to Minitab, Stat, Basic Statistics, 2 proportions. Again, we have summarized data. Sample 1 is the private schools. They had 13 out of 200 say they had been bullied. Sample 2 is the public, and they had 38 out of 300. Options, we are doing 95%. We're trying to claim that it is less, because we're saying that private schools is less than public schools. We estimate them separately. Okay. Okay. Then we scroll down to our test results. I'm going to copy them over to the paper. Again, we are reading the values for the normal distribution or the normal approximation. So I find that my Z is negative 2.38. The corresponding p-value is 0.009. Step 4, as always, is to make a decision. We're going to compare the p-value to alpha. The p-value, which comes from Minitab, is 0.009. Alpha is 0.05. I compare it digit to digit. For both the p and the alpha, the first digit after the decimal is a 0. The second digit in the p-value is a 0. In alpha, it's a 5. 0 is less than 5, so p is less than or equal to alpha. When p is less than or equal to alpha, we reject the null. Okay, thinking about what that means. If I reject the null, that means the null is false and the alternative is true. So based on the evidence that we have, it does appear that private schools have less bullying incidences than public schools. So then we write our conclusion. So step 5. We would say at the 0.05 level of significance, private schools have less bullying incidents than public schools. Questions? Okay, so that gets us through the discussion of one proportion and two proportion z-test. We have about 45 minutes, and so I want to go ahead and begin the chi-square discussion. There are actually 3 different chi-square tests that we're going to talk about. We will talk about goodness of fit. We will talk about test of independence. And I believe the third one is called test of homogeneity. The first one of those, chi-square goodness of fit, we talk about in Stat 1401. We don't talk about the others. Okay, so those 2 will be new. But we're still talking about hypothesis testing. It's not going away. So let me stop the share for a minute and go over to the PowerPoint for chi-square. While I'm doing that, do you guys have questions?
No questions.
Okay, give me just 1 second. Okay, we're going to begin with kind of an introduction, an overview of what is chi-square. And then we'll get more specific. Okay, so I'm going to share my screen again. And I've pulled up the chi-square distribution PowerPoint. It's the introduction PowerPoint. It's in D2L. So let's talk about the chi-square distribution. The symbol for chi-square, chi is a Greek letter. It looks like kind of a fancy X. And we put an exponent of 2 on it because it's called chi-square. So to indicate the square, we put the exponent of 2 on it. So that's the symbol you'll see for chi-square. Chi-square actually has several different uses within statistics. I believe we saw it earlier when we were talking about, I believe it was 2K's test, I believe. We saw it used there. One of the ways that chi-square can be used is it can be used to test a claim about a population variance or a population standard deviation. We've been talking about for a long time about doing hypothesis tests, and most of those have dealt with either the population mean or a population proportion like we just finished talking about. But we could also test a claim where we were talking about the variance or the standard deviation. And if we do that, we would apply or use the chi-square distribution. That particular test is used with quantitative data. We're not talking about that particular test. Guys, you can actually take an entire course on chi-square. Okay, Ms. Ralston's been there, done that. So we're only again skimming the surface and talking about a little bit about some of the uses for this particular distribution. The second one is called goodness of fit. And one of the reasons we talk about goodness of fit and the test of independence and the test of homogeneity is they are tests that can be used with qualitative data. Remember, we talked way back at the beginning of the term that we have 2 types of data. You have quantitative, which is numbers, And there's a whole lot we can do with numbers. But on the other hand, you have qualitative data, which is words. And when you have qualitative data, the types and number of analyses that you can do are limited because you can't do as much with words. But the three that we're going to focus on in this course are goodness of fit, test of independence, and test of homogeneity. So goodness of fit, it goes with chi-square, and it tests a claim that an observed frequency distribution fits or conforms or follows a particular distribution. We may want to say that everything is equally distributed, or we may want to say that each one has a certain percentage. And we'll talk about that when we get to goodness of fit. But again, we're taking an observed frequency distribution, and even more specifically, it's a categorical frequency distribution. The third way is, well, and I give you some examples here. I'm sorry, I didn't realize I had done that with goodness of fit. A third way we use chi-square is with the test of independence. Test of independence lets us determine if there is an association, almost like thinking about it in terms of a correlation, like we did with numbers, but we're looking to see, is there an association or a correlation between two qualitative variables? And those two qualitative variables are presented in a contingency table or a two-way table format. So again, it's similar to the idea of correlation and regression. So some examples might be, is the stop smoking method independent of success, whether they quit smoking or not? Is there racial profiling? Is being stopped by the police independent of race and ethnicity? Test of homogeneity. Test of homogeneity looks at a claim that different populations have the same proportion of characteristics, that they're similar in their makeup, even though they're two totally different populations. Maybe you're looking at people within the United States and people from Europe, or you're looking at, you could even do males and females. So you're looking at two different populations, but trying to determine if they have the same proportion of test statistics or same characteristics. Again, one of the primary reasons we're looking at test of homogeneity is because it lets us examine or analyze qualitative data. Some examples might be, is the proportions of agree, disagree on a survey the same for men and women? Are checkout scanner error rates the same for regular priced items and advertised special items? Okay, so those are some examples, and it also gives you on this slide, these slides, examples of how the question might be worded, because I suppose one of the challenges you may have is identifying when to do test of independence, test of homogeneity, or goodness of fit. Just a little bit about the chi-square distribution. Chi-square is similar to the F distribution that we used for ANOVA. It is not symmetric. In fact, it is skewed to the right. And this graph over here gives you several different ones depending upon what's called your degrees of freedom. The mean is going to be just to the right of the peak. But because it is not symmetric, in fact, it is right skewed, your values for chi-square will always either be 0 or positive. They'll never be negative. The shape of the distribution is determined based on the degrees of freedom. And we talked about degrees of freedom early on, that's the number of values that are free to vary after a sample statistic has been computed. How many values can you choose before your statistic becomes predetermined? And it's different depending on whether you're doing test of independence, test of association, or goodness of fit. So the way it's calculated is different for each of those tests. Normally it's related to how many categories you have. And again, just like we've seen with a lot of our other distributions, chi-square can also be approximated using a normal distribution if you have a large enough degree of freedom. The primary thing to remember about chi-square is that it's not symmetric, so that your values for the test statistic should be 0 or positive all the time, every time. Okay, so that's kind of a broad overview of the 3 different tests. Now we're going to shift focus and look just at chi-square goodness of fit, and we'll see how far we can get. We have about 35 minutes left. So chi-square goodness of fit, in terms of the requirements for it, again, with this, we're going to be using qualitative data. So you're talking words or phrases. The data, again, as always, should be randomly selected. Your sample data is going to be the frequency for each category. How many do you have in each category? It's the frequency count. That's your data. We'd love the expected frequency for each category to be at least 5. Normally, Minitab will indicate if that is not the case. It's not a deal breaker, but again, that's the ideal. Expected frequency, again, we have that's kind of a new term, is the frequency that would occur if the data actually followed the distribution that we claim. Okay, so you're going to kind of have the observed, what really happened, the reality, and you have the expected, which is what should happen theoretically, in theory, if everything worked the way it was supposed to. So the expected frequency is the frequency that would occur if everything worked the way it was supposed to, based on the claim or the distribution that we're using. There's a formula for calculating the expected frequency, but Minitab also does it for you, and I'll show that to you when we get there. The formula is your sample size, which is n, times your proportion. Okay, so it's the number of observed values in your sample, so the total sample number, times the probability of success, which we just learned is P. This is the formula for chi-square. Please do not freak out on Miss Ralston, because Minitab is going to do it for you. But basically what we do is we compare what we observe in reality to what we expect in theory. And we look at that relationship. Okay, don't freak out about the formula. Minitab's going to do the work for you. O is for observed, E is for expected. And you have to do that for each category, and then we total them up. Our hypotheses are typically written in words, and the null hypothesis will always imply equal. You don't have to worry about less than or greater than. The null hypothesis will always imply equal. We usually state it in words, and there's different ways to state it. We can say the population fits the given distribution, or it follows the given distribution. We could also write it out in symbols and indicate that each proportion is equal to the other one. The alternative hypothesis will always imply not equal, that they're not the same. Again, we typically state it in words, and the options would be that it does not follow the stated distribution, or it does not fit the stated distribution. Or if you're writing it in the symbols, we would just say at least one of them differs. Because if one is different, they're not all the same. The process in terms of hypothesis testing is not changing, okay? The process is not changing because you're still going to state the hypotheses, identify the players, calculate the test statistic, make a decision, and write a conclusion. There are two different scenarios that we see with chi-square goodness of fit specifically. We can talk about the data or the population being equally distributed, or we may be given a specific distribution. So we're going to talk about both of those. Process doesn't change, just a matter of what information you have to tell Minitab. The Minitab instructions for equal proportions are on slide 6. Okay, they're on slide 6. And then we have an example. So I'm going to see if I can pull the examples up in a Word document. I think I already have them set up. So let me see if I can do that. Okay, so these are our chi-square distribution examples. And this document is in D2L. I'm going to make the print bigger so I can see it and you can see it. Okay, so let's look at this one first. It says, employers want to know which days of the week employees are absent in a 5-day work week. Most employers would like to believe that employees are absent equally during the week. Suppose a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences. The results were distributed as follows. The population, if I can make that bigger. For the population of employees, do the days where the highest number of absences occur with equal frequencies during a 5-day work week. Test at a 5% significance level. Now, again, one of the first decisions you're going to have to make is, oh, I need to do chi-square goodness of fit. So you have to kind of have an idea of how do you know to do that. Well, one clue is that the data is given as a frequency distribution. Okay, this is my data, and the data is presented as a frequency distribution. It gives me the days of the week, Monday, Tuesday, Wednesday, Thursday, Friday, and then gives me the number of absences. The number of absences here is your frequency. And the days of the week, of course, are your categories. So that's one clue that is probably going to be a chi-square. But then also think about It says in this story that the managers were asked which day they had the highest number of employee absences. So the response that they're going to give is going to be a day, which is words. Okay. In this case, you really only have one category, being the category being days of the week. And so again, that's what helps me to recognize that this is going to be chi-square goodness of fit. I realize we've only done goodness of fit at this point, but for test of independence, you have a contingency table. This is not a contingency table. For test of homogeneity, it's usually a paragraph, if I'm not mistaken. It's not presented in a table form. So the fact that I have this frequency distribution that displays my data is really the biggest clue that this is chi-square goodness of fit. So then we begin the hypothesis testing process. Y'all have got to be tired of hearing Ms. Ralston say that by now. Okay, first step is to state the hypotheses. You're going to have your null hypothesis, and I just told you that your null hypothesis will always imply equal, and then you'll have the alternative hypothesis, which will always imply not equal. And for chi-square goodness of fit, I know that in your homeworks and on the final exam, it's written in words. Okay. So we got to try to figure out what our hypothesis is going to be. It says, for the population of employees, do the days where the highest number of absences occur with equal frequencies. Okay, so the question is, do the days, are they equally distributed or not? Okay, the claim here is the days occur with equal frequency. Okay, so I see the word equal, and since that's equal, that has to be the null, and I can literally write that sentence: the days for the highest number of absences occur with equal frequency during a 5-day work week. Okay, I literally took the question and wrote it out as a statement, and because it says equal frequency, it is the null. Then my alternative has to be the opposite of that. So it would be that they do not occur with equal frequency. So we'd write the same sentence and add a few extra words. The days for the highest number of absences do not occur with equal frequency during a 5-day work week. Okay, I added the two words do not, which would imply they're not equal. Everybody okay?
Yes.
Step 2 is to identify the players. The players here, you've already been given the frequency distribution, because that frequency distribution is your data, and it's given in the problem. We do need our alpha, which is the level of significance. And then you need the confidence level. Okay. And I think I have these problems printed out, so I won't have to keep toggling back and forth. Let me double check. Yep, here they are. Okay, so I have my table. Okay, here's my data. This is my data, the table that's given in the problem. It says test at 5% significance level. So my level of significance is 5% or 0.05. And then my confidence level is 95%. Now, the other thing that you may want to make note about, it's not really a player, but the other thing that you may want to make note about is that this is equal proportions. Because the question says, do the days for the highest number of absences occur with equal frequencies? They use the word frequencies. I'm using the word proportions. That's important to note because that determines part of the command that you're going to use in Minitab. So then step 3 is we're going to calculate the test statistic. And the test statistic we're going to calculate is chi-square goodness of fit and its p-value. Now, Minitab is going to do that for us. Okay, Minitab is going to do that for us. The instructions are on slide 4 of the PowerPoint for chi-square goodness of fit. So before we can do anything in Minitab, we have to enter the data. So I'm going to toggle back over to this slide. It tells you enter data first. You should have 2 columns when you're finished. In the first column, you will have the categories, and in the second column, you'll have the frequencies. You basically have to enter this frequency distribution table into Minitab. So I'm going over to do that. Okay, so I'm in Minitab. In the first column, I'm going to put the days. So I have Monday, Tuesday, Wednesday, Thursday, and Friday. Then in the next column, I'm going to put the number of absences. And you may want to indicate that this is your observed. The observed is what you are given. The observed is what you are given in the table. Okay. And so I'm going to enter those numbers. Monday, there were 15. Tuesday, there were 12. Wednesday was 9. Thursday was, whoops, not 99. Wednesday was 9. Thursday should be 9. And Friday, again, is 15. So I've entered the data. I basically, again, have recreated that frequency table that was given in the problem. I've made it go vertically as opposed to horizontally, but that's what I've done. Okay, now we're ready to do our calculations. Stat. You're going to scroll down to tables. And we want chi-square goodness of fit test one variable. Stat, tables, chi-square goodness of fit test one variable. It asks me, where are the observed counts? Those are the numbers. They are in column 2. Then it asks me, where are the category names? Those are the days. We don't do anything with categorical data. We're going to test the input column. And for this problem, we have equal proportions because of the phrasing of the question. It says equal frequencies. We have equal proportions. Now, in this particular test, it does not ask you for the level of significance. I don't have to enter that. Once I've told it where the observed counts are, where the categories are, and the fact that I'm doing equal proportions, I'm good. I'm going to click OK. Now, I want to show you a couple of things from the results. I mentioned a minute ago that Minitab calculates the expected frequencies or expected proportions. Okay, so let's look at this table under observed and expected counts. Okay, you have the category that comes from your frequency distribution. You have the observed that comes from the frequency distribution. Minitab has figured out your test proportion. If you care, you have 100%, and we had 5 categories because there are 5 days of the week. So 100% divided by 5 is 20%. So I would have expected, if this distribution is equally distributed, my expectation in theory is that I would have 12 absences per day. Notice that value of the expected is the same for every category because we're assuming it's equal. So Minitab does calculate the expected values. I point this out because I happen to know that on the homework and on the final exam, you're asked what the expected value is for a specific category. Minitab is doing it for you. So if I needed it, the expected value here is 12. And it's the same for every category because we're saying equally distributed. The other piece that I really need is this chi-square test. This is actually my test results. Okay, my chi-square test results. From this table, I get my chi-square test statistic. Okay, this is my test statistic, chi-square. And then next to it is the corresponding p-value. So in this problem, my chi-square goodness of fit test statistic happens to be 3. The corresponding p-value is 0.558. So there's my test statistic and my p-value. Step 4 is we make a decision. By comparing the p-value and alpha. The process has not changed. The p-value from Minitab is 0.558. Alpha is 0.05. Comparing those digit for digit. The first number after the decimal in the p-value is 5. In the alpha is 0. 5 is greater than 0. P is greater than alpha. Because P is greater than alpha, we fail to reject the null. If we fail to reject the null, okay, fail to reject the null, that means the null is true and the alternative is false. Okay. So based on the evidence that we have, the days for the highest number of absences do occur with equal frequency during a 5-day work week. So we're going to say that. That's the last step in any hypothesis test, is to write the conclusion. At the 0.05 level of significance, the days with the highest number of absences occur with equal frequencies during a 5-day work week. Now, I tried not to go too fast, but I also wanted to try to finish this example. I don't have time to do another example because we only have 8 minutes, and I don't think I can get through another one. So we will pick up this discussion of chi-square goodness of fit and the other chi-square test on Wednesday. I hope we're able to finish it. And I will be posting I'll be posting a review sheet to help you get prepared for the final exam. We are scheduled to meet Wednesday, which is April 26th, and Monday, May 1st. Just so you'll know. Do you have questions before we go?
No questions.
Okay, guys, if you don't have other questions, we will finish up for today, and then I will see you on Wednesday. I'll get the recording processed and get it posted up for you guys.
Okay. Thank you for today's lecture.
You're very welcome. Y'all have a good afternoon.
Okay, you too. Bye.
Bye.
Thank you.
You're welcome.